because you can't put out battery fire. It's a chemical reaction. It doesn't need oxygen to burn. So when people say it needs 30,000 gallons of water to put the battery fire out, that's just how long it happened to burn while you were dumping water on it. But all in all, it actually makes it worse. So you can put an EV battery in a pool and it just burns. There's nothing you can do to stop it.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Joel and Brian from Scalar Performance. You may not have heard of Scalar Performance. They are a relatively new startup who have wholeheartedly embraced the application of EV into a motorsport environment. Now, I know you're probably thinking, hey, there's plenty of people taking their Tesla Model 3 Performance out onto the racetrack and cutting some laps. However, production OE-based electric vehicles have some restrictions that really don't make them entirely suitable for racetrack use, particularly if you want to actually get involved with professional motorsport in a series. On the other hand, what they've done is they've taken the Toyota GR86 and they've basically stripped the entire running gear out of that vehicle and they've made their own bespoke electric race car. Now, this is a platform that makes a lot of sense given how successful the 86 is in just about all forms of motorsport, but they've produced this to also compete with the likes of factory-built GT4 race cars. So don't think of it so much as an underpowered Toyota GR86. This is actually something that can compete at the same level and even above factory-built GT4 race cars, and that is no joke. In this interview, we talk about the development of the car, how they chose the GR86 platform in the first place, what's involved in actually building a production-ready, series race-ready electric race car, and the pros and cons of this type of vehicle in comparison to conventional internal combustion engines. Now, I know this might ruffle a few feathers. Every time we post anything about electric vehicles, we tend to get swamped with a bunch of people who have pretty negative views, and I'd like to suggest that if you're in that camp, you listen to this interview with an open mind. Like it or not, electric vehicles are only going to become more prominent, and if you're interested in using an electric vehicle in a race application, then there's a lot of great information in this interview. Before we jump into our interview, for those who are new to the Tuned In podcast, HPA is an online training school. We specialize in teaching people how to tune EFI, how to build engines, how to construct wiring harnesses. We also cover race driver education, fabrication, 3D modeling, and CAD, just to name a few of our topics. All of our courses are delivered via high-definition video-based modules that you can take from anywhere in the world, provided you've got an internet connection. And once you've purchased a course, it's yours for life, meaning you can review it and rewatch it as many times as you like. Learn from the comfort of your own place and learn at your own pace. You'll find a full list of all of our courses at hpacademy.com/courses, or alternatively, there will be a link in the show notes. And as a podcast listener, you can also use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. Again, that coupon code is in the show notes. Lastly, if you like free stuff, then head to hpacademy.com/giveaway. This will take you to the page with our current giveaway, where we partner with some of the biggest names in the performance industry, giving away high quality product that, if you win, we will ship to your door regardless whereabouts you are in the world. There's no catch with these giveaways, and there's absolutely no requirement for a purchase, and best of all, you've got a really good chance of winning. So make sure that you get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Joel and Brian. Don't have two guests too many times, so this will be an interesting experience. We'll start, as we always do, by finding out how you guys individually got interested in the automotive industry. Name out of a hat. Let's start with you, Joel.
Yeah, so basically my automotive history started back when technically when I was born. Right after that, my first word was car. My mom keeps relating, like, you've always been into cars. That was your first word you said. So that kind of led into everything. I was always, every spare second I had in high school was in the automotive room. I wasn't really too much into sports, even though I'm 6'7". I was very much into taking cars apart. That led into me being the guy to fix the cars for all my friends. Then I got into drifting, was actually my background there. I had a right-hand drive 300ZX, Z32, probably the worst car you could have picked for drifting. But needless to say, I had it, and that's what I took out. Me and a bunch of other friends with right-hand drive JDM cars. We just started renting the track. This was back in 2009. And then that led into just opening a performance shop where I had mechanics working for me. We actually started doing motor swaps, a lot of LS swaps, building our own harnesses and swapping. But we were in a kind of a small town, so I did have to facilitate actually funding the building. So in a town of 50,000 people, there's not a lot of people who really want to do that. So I would be in the back doing the builds, the race car builds, and then in the front shop, we would have grandma's Camry or a FedEx truck getting an engine. So that kind of led up to the point where I had met Brian. And Brian had come to me with a 350Z that we had done up as an endurance car. Brian had already done a bunch of work to it. He came to me because he knew I was a Nissan guy. And we led into building the motor, and then we started endurance racing. And this was back at the end of 2020 when we first started talking. 2021 was the first year we started endurance racing. We started racing together, and lo and behold, a VQ35DE isn't the most reliable engine out there for punishing it.
Nor the most powerful engine, I'd have to say, given that we've raced one for a number of years. They're an interesting engine, but definitely not the most powerful thing out there.
So not only us having problems, like engine things, the chassis was great. Suspension, brakes, dialed in. The car was amazing. Electronics worked great. So we had engine problems. Everyone else, at least two other teams, had an engine out of their car. So we're like, what if we took the reliability and torque and performance of an EV motor and put it in a race car? Battery tech's not quite there for an endurance race, but why don't we take the reliability and low maintenance costs and power of an EV engine or EV motor and put it in a car? So that's when we got together and we're like, hey, why don't we join forces and start this EV company? Because we looked around, you can't race a Tesla on the track, or you can do some time, like little time attack autocross stuff, but you can't go door to door with an EV car to an ICE car. Just sanctioning bodies won't allow it. It's not safe because safety is not built into it. So that's where we came up with Scalar Performance. How can we bring the EV performance? And we wanted that raw feeling. We want a power delivery that's not having nannies and computers saying that, no, you can't turn that fast because you're going too fast. We don't want traction control, so our car doesn't have that in it. If you want all the power of the car, you control it with your foot. If you want all the braking of the car, you control it with your other foot. So that's what the Scalar Performance was about.
All right, about a million things that I want to dive into, but before Brian falls asleep here, let's bring Brian in. Obviously, we've got to the point where you and Joel kind of got together, but give us your background up to that point.
Yeah, so I'm a bit older. I'm in my late 40s now. So I started, in my late teens, early 20s at motorcycle racing, actually. So road course racing, sprint races, campaigned at ZX6 back then. And my whole career has been in IT. So I ran a consulting business, a large cybersecurity business. So my background's all tech, but I've always been, first motorcycles, and then once I got too old for doing that, moved to cars. And as Joel mentioned, when I built this endurance car, I had his brother do a cage for me, and I'm pretty good at fabricating in electronics, but wanted someone to build a motor, and that's how we met. And then we ended up doing a lot of racing together, and we really saw this market opportunity. And it's kind of a great mix of Joel's race car building background and my tech background, because you really do have a lot of technology in an electric car. But to Joel's point about what's in the market today, the people's complaints about electric cars being soulless and boring and too much ADAS is legitimate, right? You take a Model 3 performance around track, and there's now some products on the market that'll disable the stability management, but the stability management violently opposes the whole process. And the cooling system's not up to the task, so you only get 2 or 3 good laps. So there's real challenges there. We're like, what if we could harness the benefits of electric, low maintenance, great torque and performance, and create a purist driving experience, something that the purists who want something with lots of steering wheel feedback, lots of brake feedback, a car that they could throw sideways if they want, they could put down lap after lap.
Yeah, I'm not coming from a place of personal experience with any of the existing, you've used the Model 3 Performance as an example. I unfortunately haven't even driven one. I've been driven in one, but I've yet to actually drive one myself, and certainly, obviously, not around a racetrack. I do get what you're talking about with the sort of nanny state in terms of sort of these over-intrusive driver aids coming in. And I mean, let's be honest, we get this on even modern IC cars as well. The GR86, which is your platform, which we're going to get into, we've got the older version of that, the Toyota 86, as our own endurance car. And I mean, as you start developing these cars, you realize that the, I'm using air quotes here, traction control that Toyota give us in stock form is absolute garbage. I mean, yes, it'll stop the car from wheel spinning, but you may as well also just turn the ignition off. It, I mean, is definitely not fast. And there's literally seconds per lap to be made by just disabling that in its entirety. So, I mean, these things exist in one form or another, almost irrespective of the platform. I think probably it is easier from a technology and tuning standpoint to have more direct and quicker acting control over the torque in an EV than an IC, though. So I suppose that's why we see this. Now, a couple of things I want to get into here, a little bit outside of the topic, but Brian, I'm interested in your transition from motorcycle racing to car racing. I mean, obviously, absolutely nothing to do with EVs here. The reason I'm interested on a personal level is basically my entire family, as I was growing up, had a massive passion for fast road bikes. And for some reason, I never inherited that. Probably a good thing because I'm still here talking to you. But, you know, do you just get to a point where you realize that your life expectancy might be a bit shorter on a motorcycle than in a car?
Somewhere by my mid 20s, like I'm in my late 40s now, but by mid 20s, you just don't bounce down the pavement the way you used to. And if you're not crashing pretty regularly road racing, you're not pushing hard enough. And in your early 20s, it pretty much just means you need an extra case of beer that night and you're fine for the next day. Like
the bike, maybe not so much.
Yeah. So, I kind of evolved from competitive racing to, just lapping days with the bike and then moving to the cars. And then, more recently, like within the last, say, 7 or 8 years, moving to doing cars competitively and, again, at a hobby level, like a club level.
Yeah, of course. I'm interested though as well, does the skill set from racing a motorcycle fast on a racetrack, how much of that transitions across to a car? I mean, obviously, hopefully a lot less wheelies and a lot less leaning in the car than what you've got on a bike. I mean, I'm guessing you obviously understand braking points, the lines through corners, and probably situational awareness to other riders/drivers. But yeah, is it just a completely, two separate entities though?
I would say a lot translates of the basics of road racing, like finding the lines and all the rest. I think what road racing a bike really makes you think about though is what the suspension's doing, that a lot of car people don't really think about. It either makes it around the corner or they don't. And I'm always kind of a little extra aware of how much weight's on the front versus how much weight's on the back and whether there was too much rebound or too much compression. Because in those things, when you lose the front end, like if your wheel slides on the front end of the bike, you tuck it and you low side, whereas a car you just move over,
you run wide,
right? Like
yeah,
the consequences are not the same, so you kind of are a little bit more tuned into what's happening suspension wise. But
no, I can understand that. All right, coming back to you, Joel, you gave us a huge amount of information in that dump there. I want to come back and cherry pick a couple of elements there. You mentioned the Z32 300Z. I just want to dive back into that. I don't want to offend any 300Z owners, but I'm absolutely going to. I had the misfortune of modifying a number of those for customers in my old shop, and I'm still missing God knows how many 10mm sockets somewhere down in those engine bays. Pretty much anything you want to do on those is an absolute nightmare. Why on earth would you choose that?
So this comes back to even kind of why I really love the EV thing. I always wanted to be different in my group of peers. Everyone had a 180. Everyone had a 240. And for good reason. They're amazing cars. Like they're just you throw an angle kit on it and you go, and this was kind of before the time of angle kits, but you put your TN tie rods on it and you modify the inners and you get a little bit more angle. Super easy, super simple suspension. But I'm like, well, that's boring. Everyone uses a 240. I'm like, what's the car that nobody uses? Oh, this big land yacht over here. Nobody seems to pick those. And I'm like, I'm going to go buy one of those.
And quickly find out why no one's using them.
Very quickly. But I'm stubborn. So I put probably 6 motors in it. And then at that point, I was like, maybe I should probably stop using this chassis. So then I ended up moving to a 240 for about one event. I'm like, well, this is fun. I see why people do it. but everyone has one. So I got rid of it. And then I got a G35 before they were popular. So I've always been, and then I did the VQ37 swap to a G35 before anyone was doing those, and then boosted it. So it was a supercharged 370Z engine in a G35. So again, and then when that became popular, I got rid of it, and now we're doing the EV thing. But the Z32, the first thing I tell a customer is we're removing the emissions because it's going to save you money in the end because that's less stuff I have to deal with. And I have like this custom wrench that I had bent in a specific way and cut a certain way because to tighten the oil feed line on the driver's side turbo, you couldn't get to it. You know where I'm
Oh, you're giving me PTSD just thinking about it. The number of customers that I used to have come into my old shop and say, I want to do this, this, and this. And you look at them and you're just sort of thinking, this guy's crazy. And you're like, oh, yeah, why do you want to do that? Oh, to be different. And we kind of just equated different to just massive dollar signs, which is really the reality. I get it. You don't want to just be going down that same heavily trodden path and look like everyone else out there with the same modified car and the same wheels and suspension. I do understand that. So it's a little bit tongue in cheek, but I mean, unfortunately as well, going away from that well-trodden path does come with much bigger bills because you don't get to just pick the off-the-shelf parts. Now, I digress. Obviously, we're a little bit away from our main topic.
No, it's very relevant to building a prototype EV.
I absolutely. That's actually a really good point. Maybe not so far off topic. One more element I wanted to just ask you about, Joel, though. You mentioned pretty quickly you sort of set up a performance shop, and I mean, that's no mean feat. I've done that myself, and it was a very steep learning curve. What were your sort of skill sets at the time? Any formal qualifications around the work you're doing, or is this all just sort of learnt on the job?
So it was definitely started as a hobby in high school, and which led into me having a co-op placement in grade 12 at the end of my high school career at Honda. So I had a job at Honda, which led into an apprenticeship there. So that's where I kind of got into working at an OE level and fixing everyday cars other than my own, which gave me a great learning experience of how the OEMs are doing it, working with scanners and computerized diagnostics in that form. That then led to a job working for Subaru. So I was at Honda for 2 years. Then I went to Subaru for 4 years, got my license. In Canada, we have to have a license to work on cars. So I got my mechanics license, went through 3 years of college for that. And then at that point, I just realized that at a dealer level, if we had an STI come in and it had so much as an intake on it, nobody wanted to touch it. I'm like, give me that. Like, I want to do the swap on it. Let me put his exhaust on it. Let me put the Cobb tuner on it. Let me mess around with things. And just at the dealer level, it was so political and nobody wanted to change the status quo. Like, it had to be a stock car. It's just your maintenance, your 100K maintenance. And I was doing more work. I'd actually hired somebody to work for me during the day because I had so much work on the side. I would work at Subaru from 8 to 5, and then I would go to my own shop and work 5 to midnight. And that's where I would work with my buddies on their race cars. I would do engine jobs, head gasket jobs, just anything to fund my really expensive Z32 addiction, which was the main part of it, right? But yeah, so that's where I got some training in some hybrid stuff. So to relate to the EV thing, I did have sort of a basic understanding of the functionality of a high voltage system in a car, but to an OEM level. So we did get known when I had my service repair facility. We were known as the shop that would work on the hybrids. So people with their Priuses and their Honda hybrids, their Insights would all come to our shop, and we knew how to change batteries and all about the fluctuation in cell voltages and how it correlated to the engine. And also we even had one customer that came in and they wanted their battery was going to be so much money. It was a Tahoe hybrid. And we talked them through actually removing the EV system. So what would involve? So because we were a specialized shop in swapping components that didn't belong in the cars, like LSs and all the sort, we got really well known for doing the different things. And that's how I gained my knowledge, all self-taught, on how to make systems talk to each other that aren't designed to talk to each other.
Sure. Now we're going to get into that element as we go through in a little bit more detail. All right, well, we've sort of got up to the point where you two came together with founding Scalar Performance. I mean, we've sort of already got a little bit of a sense of this, but let's get sort of the 30,000 foot view of Scalar as it is today. So how long have you been in business, location, size, number of staff?
I think it was PRI 2022, where was it 22, 21, 21, PRI Performance Racing Industry Show in Indianapolis. We were there together, and there's rows and rows of pistons. If you have an LS, you could have any variety of piston, and we're like, this is cool. But we went to the EV space, and there's like a handful of companies there, a couple DIY builds that were super sketch, and there's not much. And we're like, why is that? We started to dive into it. So that was really the genesis and where we met Hypercraft, who is the company that we've been developing our powertrain with. So Hypercraft, which is where we are right now in Provo, Utah, we met them and we just kind of started off that relationship, and we really saw the opportunity.
So fairly fresh, fairly new business at this point.
Yep.
So just the two of you got other staff on board as well?
There's 5 of us now.
Okay. Can you give us a rundown on what those roles look like for the people in the business?
Sure. So Joel and I guess, are the primary on making the decisions and a lot of the fabrication work. We have another lead tech who worked with Joel in his past shop, and who's an amazing fabricator in tech as well. Then we have somebody who's managing the social media, and we have actually another partner in the business who's also had a lot of success in the tech industry, who's really helping with strategic initiatives there. And then part of the reason we've made as much progress as we've had is the key partners that have come to the table to just help us. So when Joel and I had this idea, and we reached out to a lot of kind of the key industry folks and said, here's our idea, we need help, and we're a startup, so we're not like an OE with lots of money. We're the opposite of that. We got amazing support from the industry. So obviously Hypercraft being the powertrain, and nothing in our EV is repurposed out of any other production car. It's all purpose built. So they've been key, and they lead to the relationships with AEM and Cascadia and what have you. But Olin's, like when we reached out to Olin's suspension, they put our car in the shaker rig and developed suspension just for our car. As well, the pickup points are GR86, nothing else is GR86. And so the weight distribution is different, just everything's different. So they've been an amazing partner. There's a company out of Indiana called Professional Awesome that's really helped with the aero on the car.
We utilize their little titanium rubbing blocks on the underside of our splitter. They make some really cool sparks. Yeah, that's the only reason we're using them. Yeah.
They're genius, aren't they? Have you seen their carbon rods for their splitter? The carbon rods that flex up, but save your splitter and when you run too much curbing or take it off road.
All right, so you've mentioned that GR86. So, there's going to be a bunch of people listening to this who aren't aware of what you're doing at the moment. So let's get the high-level view of what this car that you're developing is. So it's based on a GR86, but...
Yeah, the only thing that's GR86 is sheet metal, subframes, steering rack, control arms. That's pretty much the whole list. Everything else is unique to the purpose of the vehicle, right? So the battery pack goes down the center where the transmission tunnel would have been, and the back seats and gas tank area. So the battery pack is a big T shape. The weight distribution is not accidentally the same as a 981 Porsche GT4. That's one of the advantages of EVs. You can move battery weight around and achieve those kind of corner weights that you're looking for. So GR86 is a 55% front, 45% rear ratio. We're exactly the opposite. We're 45 front, 55 rear. So the car you get to use all the rubber of all 4 corners when you're braking into corners, because you have that extra weight in the back, right? The motor sits directly above the rear subframe and then drives a single gear reduction. So it's direct drive to a Torsen limited slip. And then the way we've designed that gearbox, it's unique to the car gearbox, but it allows us to use the GR86 stub axles and pick them up in the stock location.
Right. So you're actually driving to the factory axles in the rear, factory subframe essentially. Okay. All right. So the intention with this is to develop this into, as I understand it, a one-make race series GR86 EV, essentially. SCR1, is that what you've called it?
Yeah, the Scalar Club Racer Gen 1.
Okay. But at this point as well, it is approved, again, as I understand it, from NASA, not the space program.
Correct. Yeah, not the space exploration. Yeah, the National Autosport Association.
Yeah, that makes a lot more sense. So we're not going to space, but you can actually race this. It's approved to race in an existing IC series. Again, am I getting that right?
Correct. Yeah, so NASA is actually the largest club level sanctioning body in the US. And so our car runs in the Super Touring series.
Okay, so basically you pick one of these up, buy it, and you've already got a place that you can go and race. You're not sort of out there in no man's land trying to figure out what you can do with this car.
Exactly. Trying to beg for permission to go somewhere.
All right, cool. And we're going to get into all of that in a little bit more detail. Before we do that, obviously, again, we've highlighted the fact that this is a startup. You've only been in business a couple of years, so everything's a bit fresh at the moment. I'm going to guess there's a bit of a battle to kind of build to, let's call it critical mass, of getting these cars built, getting these cars sold and on track, because everyone's always a little bit reluctant to purchase something that's brand new and there's no one else there as sort of proof of concept that it's working and doing what you say. Let's fast track. Let's say everything goes how you're expecting. What's the sort of 5 and 10 year sort of horizon look like for Scalar Performance?
That's a tough question to answer because if we're honest, we can barely see past SEMA, which is only
A couple of months, that's okay?
41 days, actually. Not that we're counting. So, it's really hard to see 5 or 10 years, but Scalar Performance, we want to be the performance shop that's new age performance. You just heard Joel's background. We're performance guys, whether it's through large displacement or electric. And, I think there's no shortage of people who can go build an LS for you, but there's a very short list of people who actually really understand how to build EV performance. And we want to be that shop. So a combination of the motorsports is the halo, proving out that we can build systems that take immense abuse, the abuse of motorsport. But as you see the growth of the company, we're looking at, hybrid systems. We're looking at bringing the modern tech to like all the places you want to add performance.
I guess as well, this is an area of the automotive industry. I mean, it's mature to a degree at the OE level, but I mean, in terms of EVs for motorsport use, it is a very fast moving industry. So I guess on that basis, trying to plan out what this industry may look like in 10 years might be somewhat futile and almost actually hamper you. I guess you're going to have to be relatively fluid and be prepared to pivot and change direction as the technology evolves. Before we jump into the GR86 build and why you've chosen that platform, I'm interested, Joel, again, coming from the background of having no first-hand EV race car experience, can you give us from a driver's perspective what the differences, pros and cons are between racing an IC car and an EV car?
So the pros and cons that I found just from me myself racing the car, the EV power delivery is instantaneous. There's no turbo spool up. There's no supercharger waiting for. There's no downshift. There's no the clunkiness of a transmission, whether how fast it is, whether it's a dual clutch or you're running a sequential. There is still that as an extra input from the driver you have to be considering. You have to be considering what gear you're in, what's the RPM range of the motor, where's my power band. Not only are you thinking about that, but you're thinking about car placement. And as I've raced, it becomes a very fluid movement, but it's just another thing that your mind is now occupied on. So by having an EV, you can remove that task from your mind, put more focus on where the car is on the track, hitting that apex, navigating through traffic as you're door to door, bumper to bumper. It gives the driver another edge that when you come out of that corner, the torque is on. The second you press that throttle, there's no delay, no question, no hesitation. It's there. The one disadvantage that I would say about the EV is that it is a single speed. So from a dig, we've designed the car to have 145 mile an hour top speed because of the tracks that we're racing in North America. Not really is there a track where you're going to end up in a scenario where your top speed is much higher than that. So we've geared it for that top speed, and the Super Touring Series is all a rolling start. So from about a 50 mile an hour, 40 mile an hour rolling start to 145 mile, we've geared the car for that. So when we do get into corners where you're at a lower speed corner, a gas car where you can drop it in second gear, your reduction for a similar power delivery like an LS, and now you have, say, an 8-to-1 or a combined 9-to-1 between second gear, the rear diff. So it is a bit more power. However, what we do notice with the EV car is our final gear reduction is a 6.2-to-1. We can carry that 6.2 all the way to that 145 mile an hour. Whereas an ICE car, once you're past third, usually fourth is a 1-to-1. Now you're down to your 4-to-1 rear end, whatever you've geared it for. This is where we noticed the EV really excelled. It pretty much maintained pace with gas cars in the corners, but once we got to the straightaway, it really surpassed. And that's where it really started to shine. Because when you look at the power delivery of an EV, the torque is instantaneous. It's 1 RPM, you got full torque. It comes up, and then it pretty much is a flat line the entire way to red line. But your horsepower keeps increasing, and it just goes up and up and up the entire way. So the faster you're going, the more power you have. And it just is an insane amount of power when you're at that top RPM of the motor. Its power band is so much more broad than a gas engine, where a gas engine, you're operating in that 2 to 3,000 RPM window. So the EV has the power delivery through the entire power band, and that's one of the biggest advantages. But like I said, you do have a bit of an advantage with the transmission in an ICE car at a really, really low speed.
Yeah. I mean, so essentially in terms of that gearing that you've had to choose there with a 1-speed reduction, there's some compromises made. Sounds like it's not really a bad compromise. From that driving perspective, you mentioned that the instantaneous torque delivery, and we know if you've got a turbocharged internal combustion engine, obviously there's some level of lag no matter how well the turbo is matched, how modern that turbo technology is. You could argue that maybe the power delivery is a lot more linear in a well-tuned, naturally aspirated internal combustion engine, but essentially EV, the power delivery, the torque modulation is faster again, correct?
Yeah, it is applying it as faster than you can put your foot down.
That must be something of a learning curve though for your first few laps. I'm assuming that you could get a little bit eager on that throttle coming out of the corner exit and end up sort of facing back the way you come if you're not too careful.
Absolutely. So especially, coming out of the corner, you do have to be mindful that now you don't have that downshift, or you don't have that momentary lag where the fuel has to spray in, all the changes have to happen. Because it's instantaneous, you got to be more gradual with your throttle application. You can't just be stabbing the throttle, because you stab the throttle and now you have full torque, and then you're spun around.
I mean, it sounds like a lot of fun any way you put it. All right, so moving on to the car that you've developed. The first question, and the most obvious question, is why did you choose that GR86 platform as the basis for your build? And was there a short list of any other platforms that you were considering?
There's definitely a long list of platforms we were considering because we were trying to figure out what would be a good starting point. But really, the GR86 ended up winning because it's a super affordable platform. We wanted to be able to sell a brand new car. So it means that we're taking the donut cars are new cars, right? This is on the Gen 2 platform. And so it's a crazy affordable initial purchase. There's a healthy market aftermarket. So if you were to buy one of our cars and get in a wreck, I mean, you can buy control arms and fenders and they're plentiful for this. So it's a really good affordable, which is a good part of what we wanted to set out for, was the ultimate club racer. And while our purchase price is certainly got an EV premium in it, we wanted to have a really low cost of ownership. You should just be able to plug it in and race. And so that was a big part of it. Also, Joel mentioned he just put a lot of LSs into these things to make them drift cars. They're a really robust platform, right? They hold the power and they rotate rather nicely. So it just seemed like a good choice.
Okay, yeah. What were a couple maybe of the other ones that sort of made that final list of choices, just out of interest?
Yeah, I mean, we looked as kind of big as a Mustang and also Civics. We'd still want a rear-wheel drive, but I mean, at the end of the day, we're just looking for sheet metal, really, and a chassis.
There's not going to be a lot of the factory car left, certainly nothing of the drivetrain.
Right. So we considered that too because they're very plentiful and fairly inexpensive. But
all right, the other obvious question that I think people would have is, well, what separates your car from buying a Tesla or any of the other OE production EV cars, putting a roll cage in it, bolting on some slicks, a bigger brake kit, some aftermarket suspension, and taking it to the track? I think you've kind of alluded to some of the answers to that already, but let's elaborate.
Yeah, I mean, the big things are really going to be around safety and just approval of race series. But safety is really the biggest one. So if you're going out with time attack and autocross, the Model 3 is quite suitable for most race bodies. Will let you take those out. But the cages you can put in them are really bolt-in. You can't weld them in, right? And with the skateboard design for the battery pack, for people who don't know, skateboards, essentially, the battery pack is the skateboard and the car just sits on top. And that means that the battery pack is pretty much your crash zone for in a road course, whereas our battery's all inside the cage. So that's a big thing. We worked with Lifeline out of the UK on a fire suppression system that's actually deployed inside our battery pack, right? Which is, you can't do that with a Tesla either. And then there's things like FIA wants to see high voltage status lights. Is a high voltage on? Is the high voltage safe? Is there any isolation faults? All that isolation monitoring. I don't know anybody making those for the Tesla yet. There's just a bunch of safety type challenges that, we've addressed in our build, which is why NASA approved it for use.
I'm guessing, though, the other big element that comes into this, which you mentioned earlier in the chat, is that if you take your Model 3 performance to the racetrack, you're not going to go out there and do a 30-minute session and have full power for 30 minutes, are you?
So in my experience with the Model 3, you have 5 to 7 minutes of full performance.
Sure. Okay. And you've addressed that with this build, and you've got full performance for how long?
30 minutes.
Okay. That's a massive difference.
So the engineering target is 45. We're not there yet. We've got a new gen battery pack that we've engineered for the car that'll go in after SEMA, which will hopefully get us to the 45. But right now, we're able to do a 30-minute NASA regional race.
Okay. These races, these NASA regional races, I mean, how long are they? Like, are you sort of 28 minutes, so you've only got, just a whisker left at the end of it, or are you comfortably in? It's a 15-minute race and, you're good to go?
It's a 30-minute race.
Oof.
And it's a bit like asking us our fuel mileage. It depends on the track, right? But we're somewhere between, we could run another 5 to another 10 right now at the end of the race. And the biggest challenge is actually not battery capacity, it's cooling.
From those who are coming from an internal combustion background, I mean, obviously we know about cooling for an internal combustion engine, but I think people probably don't have an understanding of how that works for EV, which we're going to get into. But before we do that, Joel, could you give us sort of a rundown on the EV package that you have put into this GR86, and then what modifications were actually required to the chassis? I mean, is it largely an untouched chassis, and battery packs and motors have been built around the physical constraints of the chassis, or are there substantial sheet metal modifications to fit these components?
So there's substantial sheet metal modifications to the floor of the car. One of the first things that we did when we got the GR86, we stripped it, 3D scanned the entire chassis, and we made sure that we avoided all critical structural components. So like the frame rails that are built into the unibody, the side rails on the frame rails also. We didn't want to impede in any safety natural crash absorption of the factory chassis. So it was important that we avoided all those areas. And if we did have to modify something, the main structural component that we may have cut out was the bracing from side to side from the subframe mounts, which we ended up replacing because we had to move those for motors, because that's where the motor sits, is right above the subframe, which we ended up replacing them, and then everything's tied together with the roll cage. So that would be kind of the biggest sheet metal modifications that we have to the car. When the battery is out of the car, we've got videos up on our socials, but you can see up into the car. You can see the dash, you can see the roof. Like, the battery is now structurally putting all the floorboards together now. It is a structural component to the car. It ties the sides of the floors together. It ties all the frame rails together. So not only, did we cut out about a sheet metal, but we also replaced it with a lot of structural integrity to the chassis.
Might be interesting, maybe jumping a little bit ahead, but what's the weight differential between the GR86 in stock form and the EV version?
So the EV version, we're about just over 3,100 pounds. This is obviously a prototype vehicle, so there's extra things that we have into it. We're going to up our capacity a little bit, and we're still going to, by the time we take some weight out of this pack, go to our new pack, still going to be floating around the same weight. We also have a GR86 that we've turned into an endurance car because the chassis is so amazing. Our GR86 gas version, we have down to about 2,700 pounds. Stripped, fully roll cage. We have a extra fuel cell in it because we do endurance racing in it. So there's a couple extra things that we have into it, but friends of ours have gotten these cars down to like the 2,600 pound mark.
A bit of a penalty that you're taking there for the EV.
Worth noting, we got more than twice the horsepower though. It is an extra 400 to 500 pounds depending on how you math it, but it's an extra 200 horsepower plus.
Yeah, I mean that's not an insubstantial amount either. I'm just sorry, I don't generally work in pounds. I'm just converting that. So 2,700 pounds, I think, is the number I used. 1,230 kilograms. It's embarrassingly light because our Endurance 8.6, I think, is currently tipping the scales at about 1,350 kilograms, and it is a heavy pig. So we've got some work to do ahead of us there. Okay, coming back to the components you're fitting there, let's go through the battery pack for a start. I mean, I'm guessing here you've talked about the T-shape, how you've gone down the transmission tunnel and across that rear where the factory rear seats sit. I'm guessing you can't sort of go to pick apart and sort of grab some battery packs out of your crashed Nissan Leaf or Tesla Model 3 and, it should be right. Pack that all together and call it good. How do you even approach this when you're building what is going to be a production off-the-shelf EV car? Do you go to a manufacturer and say, hey, look, this is what we need. Can you build me something to suit?
Well, the good news is our partner Hypercraft does this for a living.
Perfect. Okay.
Yeah, so that was a big thing. We came to Hypercraft, and they have a pre-made module. Basically, they gave us the space claim of this is what your module is, and then in 3D space, we orientate the modules in a way that suits the chassis, is inside the roll cage, keeps a weight balance low. So even though we do have a bit more weight, the center of gravity is much lower in this car, and you do feel it as you go through the corners. So that was really key in how we placed the modules, and we probably went through 20 different renderings in 3D space before we came up with okay, this looks like a good model. We built the battery box, we fit it in the car, and then we're like, well, that's not going to work because now it hits your arms. We had a space where the throttle pedal would have bolted on, but you couldn't push the throttle down because it would have hit the battery pack.
That's kind of important.
Details, right? So we went through a lot, probably about 3 or 4 physical actually just empty hollow boxes inside the car to get the ergonomics. We didn't want to take up space on the passenger side because you don't exactly spend this kind of money on a car and not scare the crap out of your friends. You want to take your friends with you also as a teaching car because you can dial the power in whatever level you want. We wanted to be able to, it was very important to have 2 people in the car. So that was important to deal around the seats, to have a seat wide enough that anybody could drive it and not only like an Evo S tiny seat, so only somebody who weighed 100 pounds could drive the car. So we wanted it to be very approachable from every size of person, every skill level of person, and also feel like a car. And a lot of people see our car and they don't even realize that the center console is the battery. We kept the height of the battery as the same as if the factory console was in there. So really you don't notice much that there is a battery beside you. You just look in the back seat and you see that there's a battery behind you.
Yeah, okay. I mean, these are things that are easy to overlook. And I mean, again, I do have experience with this chassis. It is a small chassis. And my business partner, who also co-drives the car with me, he's a big boy. So I've gone through that sort of trying to fit a bigger seat into what is a small car, not ending up having to cut into the transmission tunnel. There's challenges there in making everything work. So what I'm picking up here, just to be super clear, this battery, these modular batteries, the battery, as I understand it from what you've just said, is not made specifically for you to suit this car, because I can imagine that being super expensive, but rather this is a modular battery system. You can orient it in a number of ways, and basically they've said, here's our modules, and you've gone through and figured out what the best use of the space you've got available to work with their battery modules. Is that sum it up okay? Or have I missed something there?
Nope. Yeah, the module itself is kind of a fixed shape, and even as we develop the battery, we've come up with a better design module as we work together with Hypercraft. We've made a module that's now actually 5 inches shorter and an inch narrower. So we can basically reduce the size of our actual pack now. So the pack size is custom to the car. It's very specific to this chassis. It would only really fit in this chassis unless you made other heavy modifications, because this ties into, it has holes in placement to pick up factory holes that are in the frame rails. So where we've picked up mounting points, because there's no way to mount the battery. A GR86 doesn't have any way to, drill here, and screw here. So we've had to make all our own mounting points, and we've used the existing frame rails to tie that in. So it does specifically tie into the GR86. It does turn the GR86 into a very nice flat bottom car. You look underneath the car, it's all countersunk hardware, and it turns into a perfectly flat bottom car from pretty much the front subframe, right behind the the splitter, all the way to the back of the subframe. So that was very important for us as well, to tie in that all the factory components is perfectly flat bottom.
Can't hurt from an aerodynamics perspective. Looking at that electric motor, this is another component from Hypercraft. I think that's what you said?
Yep.
Okay. Is this just the simplest option for something bespoke to go with an aftermarket manufacturer like Hypercraft? I mean, again, I don't say that this would be a suitable option for what is a production EV car, albeit based on a different chassis. A lot of people in the home-built space are swapping in Tesla powertrains into all manner of cars. And I only use Tesla as one example, but that's not a viable solution. Looking at one of the OE electric motors and then using your own electronics to control it.
So Hypercraft has a sub-brand called Stealth EV, and Stealth EV is their direct-to-consumer brand. So if you search for Stealth EV, they sell DIY kits and they sell the motors and inverters and those kind of things. And so Stealth EV is actually the branding on our motor. It's a Borg Wagner core in a housing designed by Stealth EV. So our motor is actually all oil cooled. People see the dry sump tank in our trunk and they're like, I thought it was an EV. Why is there a dry sump? We're like, it looks like a dry sump tank because it is a dry sump tank. It's a dry sump cooled oil, like an oil cooled motor. And so, but that was designed by Stealth EV, but people can go buy these motors from Stealth EV now.
How's the price point of these sort of changed? I mean, again, it is a relatively new industry, understandably, but if someone's looking at an EV conversion, and I mean, I know it might have been 2019, I was looking at some of the Cascadia products at PRI, or it might have been SEMA, I can't remember which, and they've got all of the options you could want to build your own EV, but at a very significant price point, which is understandable. So at least at this point in time, or that point in time, it wouldn't have been financially viable for the average enthusiast to go down that path of an aftermarket electric motor, inverter, controller, etc. I'm assuming that's still the case, or is it gradually changing?
It's very gradually changing. I mean, most of the Tesla stuff, they've got enough volume out there, and so many of them get written off that they're reasonably plentiful to get access to. But for brand new, there's still a healthy premium on the powertrains. I mean, you can check the Stealth EV website and look at what the various kits cost, and then decide based on the horsepower what it would cost as a gas equivalent. Make that decision yourself. But I would say, as a general statement, you could just look at the consumer market space and what OEs charge. Like, there's probably a 25% premium for an EV over its gas equivalent in the consumer, market.
I mean, I suppose you could kind of compare it in the ICE world to, engine swapping something out of a crash production car or building a bespoke race engine. I mean, they don't come at the same price point. So, that's the best comparison I can probably give there.
I have a Subaru motor that literally has $50,000 worth of parts in it.
Yeah, that sounds about right. I can imagine it's probably still not bulletproof, right? It's still not going to last forever.
I think that's pretty safe to say. But like, knock on wood, it's holding together. So just
keep your fingers crossed. Okay, so what was involved in, we've talked about the battery pack design. What was involved with working with Hypercraft to get this Stealth EV electric motor and the direct drive, the reduction drive, the Torsen LSD in a package that was something you could fit into the 8.6? Or again, was just an off-the-shelf option and then you had to figure out how to work with it?
No, everything was a collaboration. Everything in this car is bespoke to it. So it was really a matter of, we want it to be a rear-wheel drive car. So where can we put a motor? Oh, well, it would be nice if it floated in space here. Okay, so how would we attach it to the wheels? Everything. Where can we put a battery? Oh, well, but that's not going to give us the weight distribution we want. Okay, like, everything was a collaboration to get all those. I often joke around, do you know the easiest way to move a motor is with a mouse, right? So, and so Joel said, like, we got one of the first Gen 2 cars to land in Canada, and actually it's on our Instagram. It had 106 kilometers on it when we stripped it.
Pretty fresh then.
We drove it from the dealer to the shop, weighed it and stripped it, and 3D scanned it, and then that allows us, what if we put the motor there? What if we put the battery box there?
Yeah, so that leads into what was going to be my next question. Building this car in the virtual world, what software package were you using to do this once you've scanned everything? And then you're alluding to there, I mean, you've got a 3D model of the electric motor, a 3D model of the battery packs. I assume, therefore, in 3D space, you can assign a mass to those components, move them around, and then get a realistic understanding of what the weight balance, center of gravity, height, etc. is going to actually look like in the finished car.
Yeah, for us, it was 3D Fusion 360.
Okay,
is kind of what we're using.
I mean, it should be perfect, but interested, how well did that sort of actually pan out once you had the car built? Did it stack up and validate pretty nicely to the virtual numbers?
Joel, I thought you'd take this, but yeah, he was alluding to the pedal box issues and all the rest. So, things worked perfect in the 3D world, and then we mocked them up and then went, I'm not driving that car. like, so there's definitely some lessons there that we learned. Like ergonomics don't render themselves in 3D space quite the same. Joel 6.7, like our cage was all designed in 3D space too. It worked out great because we now get the cages, we can reproduce them consistently. They're CNC cut and bent, but like all this stuff, like works great in 3D space. But sometimes there's yeah, but my head fits up against that bar. That's not cool, right?
Yeah. Yeah, I guess there's nothing really quite compares to actually sitting in the finished product and realizing what you like, what you don't like, and where the problems may lie. But I mean, that is also part of the prototyping journey, I guess.
It really is. And so you can do a ton in 3D space, and then you just have to mock things up. And even our gearbox, we 3D printed it first, just a plastic shell. Will this actually fit in the subframe in real life, and how will that interfere with, would it interfere with the trunk in what ways, or cross members in what ways? We can see that in 3D space, but once it's all done there, you 3D print the housing and then mock it up in real life and go, yeah, no, that's what we expected, or we didn't foresee this other thing, right?
I mean, having been in this industry for 20 plus years and seeing these technologies come about, 3D scanning, the use of 3D modeling software, SolidWorks, Fusion 360, Inventor, etc., 3D printing coming down to a point where it's so accessible at the enthusiast level. I mean, I'd argue it's never been easier to build a car and have the confidence that it's actually going to perform as you'd expect pretty much out the gate, as opposed to back in the day where really it was all hand-drawn bits and pieces and trial and error.
A welder and a 4.5-inch grinder does many things.
and a hammer. We always need a hammer in the toolkit as well. But yeah, I mean, never has it been easier, and it's just a testament to all of this technology. But this technology also filters down because a lot of it, maybe 3D scanning aside, but we can even do that now with most cell phones. So, it's available to the enthusiast market. You don't have to be pouring hundreds of thousands of dollars into plant and equipment in order to be able to use this technology. Right, coming back to our package here, I want to talk about the other components that go into an EV system, because again, most of our listeners might not be sort of up to speed with all of this. We currently are working on an EV course, and I've got a modest level of understanding here. I'm definitely not claiming to be the expert, but the next component I want to talk about is the inverter. Maybe start by explaining what the hell is an inverter and why do we need one?
So like the inverter, to store energy, you need a DC pack. So your DC battery pack, we have an inverter to take the DC voltage and turn it into a 3-phase AC voltage. Our motor is a 3-phase AC motor. That's how we get our good power delivery and torque. That AC motor is the best application. All modern EV vehicles are also AC motors. It just gives you the best bang for your buck for the type of voltages that we're dealing with. And our car is an 800 volt system. So we're taking that 800 DC voltage into the inverter, inverting it to an AC signal. So that's what the inverter does.
Okay. Again, these inverters, as I understand them, these need to be, I guess for want of a better term, tuned to the electric motor that they are going to be controlling as well. So this isn't just a cherry pick this component from this manufacturer and the inverter from another manufacturer. It's a bit more involved than that. That inverter actually has to be calibrated to suit the electric motor that it's going to be controlling, correct?
That's correct, yeah. So as we call it, motor characterization. So the motor, that inverter, it's kind of like, think of it as like a base map for your engine. Your ECM needs to have a base map to run that engine. Every engine has a different crank signal, a different trigger. That all needs to be baked into the inverter. So when we flash the inverter with a firmware, it has the characterization for the motor that we're using. And then once we flash that firmware onto it, then we have a couple of settings that we can change that are not baked, that we can change our red line. We can change where the trigger is on it. Just yesterday, we were fine tuning basically think of it as your ignition timing on an ICE engine. Basically, where the rotor sits inside and where that pickup is, we're advancing or retarding because manufacturing tolerances are not perfect. That the pickup points might be ever so slightly off. So we drive the car, you see where that degree offset is, and you just basically calibrate it, and you're just matching the trigger points. But yeah, there is some certain calibration that you need to do in the inverter, and we look at that as like the master calibration. That is your fail-safe, our VCU in the car. So it's a vehicle control unit, is where we really make all our red lines, other torque mapping in that. But if those safeties fail and you hit a safety in the inverter, it gives you a hard stop.
That's sort of an overriding safety backstop.
Exactly, yeah.
Yeah. You just mentioned you're doing some of this fine-tuning yourself, but the high-level stuff, characterizing, as you mentioned it, the inverter to the electric motor, is that being done by yourselves, or is Cascadia, I think you said Cascadia, the inverter manufacturer, are they doing that work for you?
So the inverter manufacturers, whether it's a Cascadia, whether it's a Dana, whether it's a Maglec, they all have pre-baked in characterizations for motors that they want you to use. We're working with Hypercraft to basically be able to make our own characterizations, because right now, the EV space being so new, you are limited to what motor you can run on what inverter because of that characterization. So once we work on the unlocking of the characterization process, which we're working with Hypercraft on that, then the possibilities are endless. You can take anybody's inverter and anybody's motor and pair them together.
I just wanted to take a moment out of our interview and talk about a package of our courses that we've put together that I think anyone who's enjoying this interview would also enjoy, and that's our track day package. And regardless whether the car that you're taking to the track is internal combustion or electric, a lot of the same principles, or most of the same principles, still apply to getting the best out of your lap times. This package starts with our race driving fundamentals course, and this course will teach you, as its name implies, the fundamentals of race driving. Now, this might seem on face value to be a simple thing, but when we come from a background of driving street cars on the road, there are some very different techniques required to get the most out of your car on the racetrack. This is understanding the lines that you will take through a corner, and how to optimize your line for a particular part of the track, how to adjust the handling balance between understeer and oversteer, how to use trail braking in order to achieve that particular aim. Also break the cornering process down so you can understand each part of that process and how to know when you're getting the best results. We also talk about some of the more subtle aspects of driving your car fast on the racetrack, such as whereabouts you should be looking, how to use tools such as simulators and onboard video in order to get the best out of your track day and make you faster. Our motorsport alignment course will teach you how to use cheap, easily accessible string alignment equipment to make your own wheel alignment changes at the track. Now, if you're thinking that string alignment sounds a little bit backyardish, well, you might be surprised to know that this is the exact same technique that professional motorsports teams use all around the world. And if you've ever been to a race meeting, you're likely to have seen race cars up on the corner weight scales having the alignment set with strings. So it is absolutely not a backyardish approach. It does work extremely well. This course also includes a step-by-step process so that you can apply this to adjusting your own alignment, making sure you get the best results while making sure you maintain the safety of your car. We're also including our practical corner weighting course. Now, this is a more advanced topic, but again, if you have been to any professional race series, you're likely to see cars up on corner weight scales. And the idea here is measuring the weight distribution between all four corners. And by adjusting our ride height corner by corner, we can move the weight around. And again, this can affect the handling balance and the consistency of the car between left and right hand corners. Lastly, we're also including our data analysis fundamentals course, and this will teach you how to use cost-effective data analysis equipment in order to improve your lap times. Be that comparing yourself to a previous lap or a previous session, or better still, putting a professional driver or a driving instructor in your car to set a reference lap. Now, this doesn't require thousands of dollars of data analysis equipment, and often, particularly when you're getting started out, less is absolutely more. We show you how to use simple devices that are under $500 in order to get big improvements in your lap time. On top of the courses, we're also including 24 months of gold membership, which gives you access to our live weekly webinars where we cover a particular topic and dive in deep for about an hour. This also gives you access to our back catalogue of webinars. There's over 300 hours of content in there. It's an absolute goldmine and one of the fastest ways to expand your knowledge on a wide range of performance automotive topics. That gold membership also gets you access to our private members-only forum, which is the best place to get reliable answers to your specific questions. That total package is normally $397 US. You can use the coupon code Scalar100 and that will get you $100 off, bringing the price down to just $297 US. Despite that, we are still giving a 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide it wasn't quite what you expected or not right for you, no problem, let us know. We'll give you a full refund of the purchase price. There are also a range of payment options, so you don't have to come up with that $297 in one lump sum. Again, we'll put a link to that package as well as the coupon code in the show notes. Let's get back to our chat now. All right, the next component in this whole system, the VCU, Vehicle Control Unit, as you've mentioned, and again, I think this one is from AEM. Explain the purpose and the big scheme of EV control of that VCU, please.
Yeah, so the VCU, think of it as like your ECM for your gas car. It makes all of the decisions as how the battery performs. It communicates with your BMS, which is another module inside the battery, which is your battery monitoring system. So the VCU makes all the decisions, executes all the safeties to make sure that I can close contactors to basically make high voltage available to you. There's very large contactors that are kind of like a relay. The VCU decides when those contactors gets closed. It's constantly monitoring cell voltage, mins, max, cell temperatures. It's taking all the data from the BMS and basically putting into a nice package where it can make the decisions on when we start to derate power to the motor, when we start to derate power delivery from the battery, make some decisions around charging. It communicates with your battery onboard charger, which we've taken as an onboard charger, moved it off board to save weight. So it's actually a separate case that we plug into the car. It interfaces with the VCU to make decisions like that. It doesn't really control body functions like lights as far as the power steering and power distribution. That we're using a PDM for. But basically anything to do with the battery, the motor control, and inverter control, that's what your VCU does.
Okay, and I guess one of the essentially more simplistic tasks here is mapping driver torque request to the output of the electric motor, correct?
That's correct, yeah.
So how does that look from a tuning standpoint? Have we simply got a three-dimensional table of driver pedal position versus, I don't know, are we looking at electric motor, RPM, and then simply a torque request number, or is it completely different to that?
RPM, speed, and throttle position.
Okay. All right. So I think we've got a reasonable understanding of that electronics package. There's a couple more elements that I want to get some more detail on here. And we've already alluded to cooling and the importance of cooling in an EV, which again, I think is one of those big areas that those transitioning from internal combustion probably don't give too much thought to. But we've got the battery pack temperature, as I understand it, quite critical. In order to get the best performance out of the battery pack, it has to be within a really tight bounds of minimum and maximum temperature. So controlling that's quite important. Am I on the mark with that one?
Yeah, absolutely. Battery temperatures are, well, there's several systems that need cooling, right? Your batteries need cooling, your inverter needs cooling, and your motor needs cooling. So kind of the three major components of the system all have different cooling needs. How they differ from a combustion engine really is where they want to live. Like in Celsius, the battery would like to live, our batteries, based on our chemistry choice, 45 to 65 Celsius is ideal for them.
Sure. Now that actually creates a problem, doesn't it? Because of course your internal combustion engine runs much hotter than that, maybe between 85 and maybe 105 degrees C. And the easy bit to overlook is in terms of the heat exchanger, the radiator for want of a bit of a term, you're looking at that temperature gradient between the coolant and the ambient air. The higher that temperature gradient is, the better the heat transfer we get, or in other words, the more cooling we can get. But if you're only at 50 degrees C and maybe your ambient temperature is 35, maybe it's a really hot summer day, you don't have much of that temperature gradient there to aid with the cooling, do you?
That is the big challenge. You absolutely nailed it, right? Is the delta between the ambient and your target temperatures is the big challenge with EVs. And the fact that motors, our motor, if it has its way, it's happy at 90 to 110, right? Much like it wants to live at combustion engine temperatures. And actually, that electric winding, the hotter it gets, the lower the resistance through the motor. It's happy at that temp, which is why we've separated it into a separate cooling system and the oil dry sump setup.
So you can then run the motor at 90, but the batteries at 50, 60, whatever you want to keep them at.
Exactly. And then the inverter wants to live basically the same temperature as the battery. So in our case, the batteries and inverter live on one coolant loop, which is water cooled, and then the motor's separate oil. And we've done a lot of work on that front because the real challenge there is, of course, the ambient to target delta that you talked about, but then also how do you get that heat from the battery cells, which are heating up, into the coolant, right? So there's a number of industry strategies for this. You can run coolant like serpentine type hoses, channels between cells. You can do what we're doing, which is chillers on the end plate, and sorry, the ends of each cell, right? Because the heat tends to build where the current's flowing, and then your collector plates tend to get the hottest. But of course, you can't put an aluminum chiller plate directly up against your cell ends. Then your chiller plate would be the collector plate, right?
Yeah, probably wouldn't work
And
too well.
that would be exciting.
In terms of the cooling strategy for the battery pack, is this something you've got a lot of input on, or have Hypercraft got their battery packs and this is how we cool them? Here it is. Now deal with the repercussions of our strategy.
So outside of a Rimac, there's not really anybody who's got a street going vehicle who can cool at any kind of track time. And so this is something that we've worked on together. And actually, we brought another partner. I was mentioning at the start, the way we've done all this development with so few people in the company is by having great partners. And so PWR, also out of Indianapolis, actually, they're an Australian-based company as well.
They're Australian, but you can
Yeah.
claim them as American. It's
Well,
fine.
their American headquarters
Sure.
is in Indianapolis. They've been an amazing partner, and their chiller plates are top shelf. So they're what's in our car, and they've been part of. So it's a three-way engineering effort between Hypercraft's engineers like us and PWR. So it's been a lot of learning for all of us.
Breaking this down though, I'm sort of reading this is one of the big differentiators between a car like you've designed, purpose built for a motorsport application, where we know it's going to be used under sustained high output for a long period of time, versus a road going Tesla where it's going to go to the track, do 3 laps, and the battery temperature's through the roof. It has to derate to keep everything alive, and you're dead in the water. Am I right with that?
That's it. Exactly.
And let's talk about that derating, because this is, again, a term you hear thrown around when it comes to EVs. From the driver's seat, what does this mean? Are we just losing sort of, 5 or 10% power, or is it 50% power or more?
So I can tell you, like with the AMVCU, we can control how much derate there is. I can also tell you from taking a Tesla out on track, the derate is, as the temperature comes up, it derates more and more. And so that you can really quite noticeably feel the car slow. Like it's less and less power available. It's like somebody's taping off your airbags, right? As you're driving around is probably the best way to describe it. But to your question before, like when you start thinking about thermals and EV, like a Tesla Plaid running a quarter mile in whatever 10 seconds, or that's 10 seconds of wide open throttle. That's not really a lot, but you're basically wide open throttle between each corner on a road course. And what it turns out generates tons more heat than like a wide open throttle discharge is an aggressive regen. Regen, like the charge function, generates substantially more heat than the discharge function.
So you need to control that battery temperature during the charge or regen.
Road course use just beats the snot out of the battery packs, whereas road use, you can just never be on throttle for long enough to really heat soak a car, right?
Yeah, I always sort of talk about this even when it comes to tuning strategies for internal combustion engines. I mean, what you can get away with for a road car it'd be difficult if you value your license to be at wide open throttle for more than 10 seconds in a seriously powerful road car. So, the combustion temperature that gets built up over that period of time is by definition limited compared to using that same vehicle on a road course where you might be at sort of averaging 70% throttle over a 1.5 minute lap, and you go out there and lap for 30 minutes, which is quite possible. That is a very, very different deal. I mean, obviously away from our EV discussion, but it just highlights those differences.
No, but it applies for a road car. Even if somebody wanted to argue with you right now, say I could do more than 10 seconds, it's going to be measured in a few minutes. Like there's no chance it would be minutes on a road.
I mean, there's levels to that as well, because I've used road car versus road course race car. Okay, that's one step. I've also been involved with tuning for Bonneville, which is maybe a few minutes on end. And then just talking to a friend of mine just recently about marathon jet boats. And those things are essentially at wide open throttle, maybe for 30 minutes at a time, give or take. Obviously, it's not quite like that. So there's levels to this heat build-up and management strategies that we need to use. But let's get back to EVs, because that's our interest today. Charge time sort of builds back into that sort of comment you just made about controlling the battery temperature during charging. Obviously, you've said you've got 30 to maybe 45 minutes of range on track. Obviously, between sessions, you're going to need to charge that, and that needs to be done quickly. And that's sort of been another one of those limiting factors for EVs in a motorsport application. How long does it take to get some charge into this thing?
So, like almost every answer we're going to give you, the answer is it depends.
Very, very political.
It depends on the charging infrastructure available. A level 2 charge at 6 kilowatt, we got a 60 kilowatt pack. That's like 10 hours, right? What we're doing for NASA events, there's generally 60 to 90 minutes between, say, practice and qualifying and that kind of thing, which turns out to be lots. So we end up usually charging the car at, say, 30 kilowatts, which gets us, if we use half a charge out in qualifying 20-minute session, we're charged back in 35 minutes.
Okay. So pretty manageable in reality.
Yeah. Now we could charge up to, I guess, 150 kilowatts. You can do the math on, 60 kilowatt pack is like not too long, but you'd shorten your life of the pack for no reason.
My question on that front is, what's the electrical infrastructure at the facility needed to run a 150 kilowatt charger?
So our kind of home base for track testing is Atlanta Motorsport Park, and they have 150 kilowatt chargers there at the track. So Atlanta Motorsport Park is very pro EV facility, and so they've got 5 of them. but mostly when we're racing, we rent a generator, a construction style generator, and bring essentially a DC power supply is how we're doing it right now. But it'll be a much more, when we sell it as a finished product, refined level 3 charger.
Sure. Okay, regenerative braking as well. I understand you're incorporating that. So this is a benefit, because when you're braking, it's essentially charging the battery packs to a degree. I'm interested more from a standpoint of what that feels like and looks like from the driver's perspective. And I understand that this is adjustable. I'm getting here about brake balance in a race car is incredibly important. And we want to make sure that our brake balance is dialed in so that we're not locking the rear axle before the front. Otherwise, you're going to sort of enter the corner backwards, which isn't going to be too quick. Yeah, how does this work, and how tunable is it from the driver's seat?
In testing, we've definitely entered a couple corners backwards.
Because of regen.
Okay, so I'm on the money here.
Yeah. Oh, yeah. So like with how we've done it, we have gone out with no rear brakes on the car. We actually completely remove them. We're like, let's go out with just regen on the rear brakes. What does that feel like? But the problem with that is, so that's a lot of power being put back into the pack. Now you cannot leave the pits with 100% charge, because what happened our first time is I went out, and by about the second corner, I went deep in the brakes, deep in the corner, and then all of a sudden regen shut off, because now my pack went over voltage.
Because it got nowhere for that power to go.
Yeah, the cells have maxed out at 4.2. The VCU is like 4.3 is too much. You're done. Shuts regen off, and now I've just lost rear brakes. But I'm committed to this corner, and now what do I do, right? So we've decided to go with an approach. We tried like medium size, so just a 2-piston rear caliper. Right now, we've kind of landed on back to the big brake, the 4-piston rear caliper, with about a 10 to 15. I think we're at 15% regen right now. So what this does is this allows us to go out with pretty much 100% pack, charge pack, because the first lap, again, it's a rolling start. By the time you do that first warm up lap, you've just depleted the cells just enough that by the time you go deep into that first corner, you have a place for the regen to go.
Yeah, okay. I'm guessing this is only really an issue for the first 1 to 2 corners because you're obviously depleting that battery pack anytime you're on the throttle.
Exactly. But what does the battery pack, that top 5-10%, mean for you in the longevity of the race? The bottom 10 to 15% is not worth as much as the top 10 to 15% because what you have is voltage sag. As the battery pack gets depleted and your voltage gets low, the battery pack will actually sag because it's drawing voltage out of it below the minimum threshold we like to see. You come back off throttle, the voltage comes back up. So that 10 to 15% is more valuable to reduce that amount to the point where we hit that voltage sag point.
So it's essentially not linear through, if we just look at literally the battery charge from a percentage basis, that's not strictly linear.
Yeah, as the battery pack depletes, the voltage sag becomes more and more and more. So we really want to optimize that top percentage of the battery pack that we can use.
Okay. All right, let's sort of move away from the electrical components for a moment and talk more about some of the rest of the platform. I mean, I'm not going to dive into suspension because, this platform is well supported. You've already talked about Olin's coming on board and helping you out there. It is a well-balanced, well-handling car. Braking system. Obviously, we just talked about that regen adding a bit of a curveball into what's happening with the rear brake package. Am I safe to assume here you've gone away from the factory ABS system? It's a full motorsport pedal box, full aftermarket sort of style race brake system?
So I'm a huge fan of depowered, no ABS race cars. I want all the feel through the pedal. I want to know if I rolled over the tiniest little pebble on track, I want to feel that through the brake pedal. And so this car is depowered, and there's so much pedal feel that we've rain raced it a number of times. Nobody has challenges with locking them up. There's immense pedal feel. And we do have a proportioning valve in there right now. But what we've found is we've gotten, more and more advanced on our regen mapping is we use regen as the bias control because our car, like the Willwood kit on it right now is the kit for GR86. So it's bigger brakes on the front because the GR86 would be a 55% front, 45 rear. So the rear calipers are smaller. But because our car is 55% rear, we actually need more brake in the back than we do in the front because we get so much more braking out of the back. But we're able to use the kind of regular GR86 Willwood kit, the 6 pots in the front and the 4 in the rear, because we get much more than those 4 in the rear can deliver by adding regen to it. And so we're able to brake bias the car, front and rear bias, by adding and removing regen.
Yeah, okay. Makes good sense. In terms of the other electronics in the car, I mean, again, obviously it's a platform that I have to have some experience with. Electric power steering, I think that's actually probably the only factory system we've now got left in our car, but that actually does require some CAN messaging to kind of do its thing. So if you remove all of the factory electronics out of the car and just leave the EPS, it's going to be a pretty heavy steering. So how have you handled that? Is this through that AEM VCU, or are you doing some custom stuff in the background?
Yeah, we just send it the messages it's looking to see. So it's essentially, it turns on with ignition really, and it adjusts the power assist, the steering assist, based on vehicle speed. So actually, interestingly enough, we can change the behavior from factory steering assist by just lying to it about vehicle speed as well.
Yeah, nice. So you've got a bit more control than in factory form.
Yeah.
So as I understand it, the electric motor that you've settled on for the time being is capable of delivering around 500 horsepower. I'm not sure if that's wheel horsepower or motor horsepower, but at the moment you're running it, I believe it around 350. Why not have all of it?
So we've got 460 at the wheels when we put it in what Joel and I like to call all the beans mode.
That's a mode that I would be wanting to run all of the time. All of the beans, all of the time.
I would like all of the beans all of the time. Well, you sound like us. But you want to be able to put down consistent laps. You don't want your laps falling off You don't want to be able to start the race doing great lap times and finish the race like 10 seconds off the pace. And so what that means is you can't have all the beans, because if your power is very simply volts times amps, well, we have an amp limit, the collector plates, the bus bars, etc., can tolerate, which is actually the limiter of why we're getting 460 wheel horse right now, not the 500 that the motor can do. But if we let you do that through the whole race, the all the beans mode, your lap times will fall off because the volts will come
So
down.
this gets back to that derating that you're talking about.
We're not derating, we're still letting you have all the beans.
But you're using the beans quicker.
Yeah. So really what we want to be able to do is pick a number so that, volts times amps is consistent throughout the 30 minutes as a wattage number output, right? So that wattage is available even when the cell drop from 4.2 to 2.8.
Okay, yeah, that makes sense. And in terms of as well slotting in with this existing NASA series Super Touring, is there a balance of performance here? I mean, I'm guessing that you're going to piss off a lot of internal combustion racers if you just come there and smoke the entire field and you're sort of a lap up from P2.
So because I prefer to make friends than enemies, but also with NASA, they've been a great partner. When we reached out to them and we're like, here's what we want to do, this is really a development year. So we're running what should be an ST3 car, running ST3 lap times, and we're just running in ST2. And if we take a place from anybody, they're essentially putting us as a just for fun run.
Okay, so exhibition essentially.
Yeah, because as we're developing the car, we don't want to wreck with anybody's championship points for the season because it's a development car, and we don't want to just walk away with the field as we're figuring things out. So essentially, we'll BOP the car once we firm up how it's actually going to perform as we get all these mappings and tables to a final state.
Okay, yeah, that sounds fair. Definitely, I don't think it'd work in your favour if you come in there and kind of ruffle all the feathers. Yeah, that's one way to get offside with just about everyone. Interested to talk about the running costs and servicing costs in comparison to an internal combustion engine race car, at a similar power level. Let's call it 350 wheel.
So yeah, as far as maintenance costs, that was a big reason why we did this. There are some fluids that obviously need to be serviced, but the nice thing about the motor that runs a Dexron 6 fluid in it is probably about 10 liters of fluid in it. You're really not changing it because you have combustion in it or there's foreign material in it. It is there just to cool a motor that doesn't make contact with anything. You have 2 ball bearings.
So it's not getting contaminated.
Exactly. There's no contamination. So the only reason to really change it is maybe because it's been heat cycled a number of times and the fluid is actually starting to break down. It is a synthetic fluid. So even in that case, really it could last for a while in there. So there's not really, I would recommend probably just changing it every year. You'll have some debris happen in there from whatever instances. The diff oil, it has a gearbox in it, so it's got gear oil in it. You'd probably change that every year. But apart from that, the motor is recommended to have the bearings changed every 1,000 hours. That's a lot of racing. You probably
won't. There's a lot of racing.
You probably won't own the car for that long to be able to service it. So really the motor remains untouched. The gearbox pretty much remains untouched. The only service we expect to see is pretty much the battery pack. And even at that, we're expecting to see probably a 5 to 6 year life expectancy just because of the extreme abuse that it will be taking. You're pretty much discharging it and recharging it while you're on track as fast as you can, ramming it full of power as fast as you can, and then discharging it full of power. It's just so violent on the cells to have that in and out that you do break the cell down. So,
oh yeah, I can understand that.
Call it the life expectancy of the battery, 5 to 6 years. That's really the only serviceable component in it. Brakes, tires, your standard there, but there's not really any maintenance costs.
Yeah, interesting. So essentially, you could call the electric motor good for life. I mean, I'm interested here, does the output from that electric motor, the power potential of that electric motor, does that have any drop off? Obviously the conventional internal combustion engine, the rings wear, you're going to start seeing additional crankcase pressure, additional blow by, and over the life expectancy of the engine, be that a year of racing, maybe a couple of years of racing if you're lucky, you will start to see a drop off in the performance a little bit. We see that on our dyno.
So that's the nice thing about the motor. You're not going to see that unless you overheat it. which we took our motor. We're like, let's see how far this thing can go. We just pushed it to the max. It actually got to over 210 degrees Celsius. So spicy, right? The car was still driving, like, and that was with a temperature gun on the outside case. So it actually had melted the nylon AN lines, but the car was still driving. It really only just demagnetized the motor a little bit. The car still drove the next day, like it was a little less powerful than it normally was. But really, that's the only kind of degradation you might see in a motor is if you overheat it. And I mean, like, really overheat it. Our D rate is actually at 180 degrees C core temperature. So up until that point, the motor is happy.
Wow. Okay.
Yeah. So when we sell the car, it won't go to that when we're testing.
Yeah. Well, I mean, that's the thing about prototyping and testing. You've got to find out, as you say, the limits there. Coming back to that battery pack, could you give us a sense of, a customer buys one of these, has it for 5 to 6 years, and gets to that point where the battery pack needs to be replaced? I mean, we hear horror stories about these in OE production vehicles when the battery packs go bad. What sort of price point is going to be a pick?
I will say though, when you're told like your Tesla needs a 15K battery pack or whatever your street car, they're all in US dollars. Like you hear numbers in the 10 to 15. That sounds like really a lot, right? But when you talk to any racer and you're like, you're gonna have to do an engine rebuild a couple times this season, it's a lot more than that.
Yeah, I mean, you've got to keep a perspective on it for sure. Yeah.
And so if we're like, you have to do the equivalent of an engine rebuild every 5 years, that sounds like a pretty good deal to me, right?
It doesn't suck.
And so I mean, we don't have a final price on the pack, but it's the cost that's driving these OE vehicles is the individual cells. We're also tied to the cost of individual cells, in our case, Samsung cells.
So we're talking there or thereabouts.
Similar, yeah.
Okay. I probably segues nicely into the elephant in the room, which is the price of this car. Connor did actually shoot a video with Joel at SEMA last year. We got a lot of comments about the price point of the car, and it's up there. What are we looking at as a production item?
So we're selling the car at 210 US dollars, and that's, I agree, a healthy investment into a club race level car. I will say though, the kind of lap times it runs, M2 competition, GT4, they're similar priced vehicles.
I think people will probably start by comparing it, and obviously so, to a GR86 or GR Cup car. And my quick research before this, 125k. Obviously, that gives you the ability also to run in that GR Cup, a single make control class series. And that's a great way. I know that you're building up towards that yourself, but that's a great way in a single car, single make class where it's all controlled. Does really highlight that driver skill rather than just going out and hitting it with an extra 100 horsepower. But the difference here is EV versus internal combustion, and you're like 100 horsepower plus up the road from the GR Cup car.
The GR Cup car is a stock motor, so 230 horse is what they're claiming, and we're 460 on the last dyno run. So, even if we, to get the 30 minutes runtime, end up, setting the car around 330 or 350, somewhere in there is where we'll probably end up for that runtime. That's a substantial change in power. And, just like we were talking about earlier around the consumer cars, there's a 25 or 30% premium for being EV right now. Hopefully you get all that money back in total cost of ownership, not doing motor rebuilds.
Yeah, I think that is an easy one to overlook. It's not just the cost of purchasing a race car, it is what that's going to cost you over the lifetime of the car. Unfortunately, most consumers are pretty blind to that when they go into purchasing a race car, and kind of, we'll worry about that on the backside when in 6 months' time we realise we actually need a $20,000 engine rebuild. But, I understand that mentality. I've been down that before. In terms of the sort of one make class for this, how far off is that, do you think? I guess you get to a situation where you've got to build up a critical mass of people with the cars we talked about earlier. Sort of, you need a bit of a proof of concept as well, which you've got obviously with this NASA Super Tourer class. Are we talking maybe a few years down the track maybe?
Yeah, because we want to make sure that this car really is just plug it in and then go race and then put it back, plug it in. And, I say to people, imagine spending your race weekend racing Like, yeah, everybody rolls. It's the same reaction you have. Like, you roll your eyes and like, that'd be amazing.
How good would that be?
And that's the goal with this car. So, hopefully we can get more of these out on track next year. That's our plan, into more consumers' hand the year after. So I think your 2 to 3 year window to run a spec class is probably spot on.
Okay. And just sort of coming back to that price point and comparisons, I mean, obviously it's a mile up the road in terms of lap time from the GR Cup car, despite obviously a significant price premium. You were talking there about lap time comparable with the current crop of GT4 cars.
Yeah, that's what we're doing right now. So we'll see where it finally ends up, right? We want to, again, get it to where there's no performance drop off over the 30-minute race. And so that's a matter of getting it to just the right number.
And, I mean, obviously it depends on the marque itself, but, whereabouts in terms of price points are the current crop of GT4s if you're buying one showroom fresh?
They're very similar in price. I haven't looked at all the sticker prices. Like an M2 competition's pretty close to $250,000, I think.
I mean, obviously the difference being you're not running a BMW/Porsche/AMG badge, and I mean, I don't know what value to put on that. And I'm not going to get into that argument, but yeah, it is obviously a significant chunk of cash to lay down. I just wanted to
I was going to say those cars that we just listed off, though, those motor rebuilds are not going to be cheap.
No,
they're not your 20K rebuilds either.
Yeah, no, definitely.
Right? Like, your suspension bits are not going to be cheap.
Well, I mean, even if we, aside from that, have a bit of a touch with another car and you need, maybe a new fender and a new door, those aren't going to be GR86 price point either.
Exactly. Like, we're very aware there's an EV premium, but it is what it is. We have to buy it for the premium and we need to pass that along. But to your point, all those bits are so much more expensive on those equivalent cars. So we're really hoping to create something that you can just buy and race.
Okay. All right, let's move on a little bit. And I want to talk about sort of uptake of EVs in motorsport worldwide. And I've kind of seen it being a little bit slow here in New Zealand. There's a few rules I think have come out around how EVs will integrate. Australia, from what I understand, is almost made it impossible for production electric vehicles to compete in motorsport race classes. What are the sort of problems with integrating EVs into existing motorsport classes?
I think it comes all down to the safety. We talked about this earlier, right? Like, FIA guidance on EV race cars is around, they need ready-to-move lights. They need high-voltage safety lights. They need fire suppression that's Novec 1230 based. They need, like, FIA's laid out what an EV needs to go competition racing, EV or hybrid.
So you can do this easily enough because you're just ticking those little check boxes when you're building a bespoke car, but you cannot really get that same result from an existing OE production EV.
That's the big challenge.
Right. So essentially we're going to see little uptake of production EVs competing in motorsport series, but maybe a few more companies like yourselves come along with FIA spec EV cars that are legal.
And or you may see people who are building full conversion kits for production EVs, right? That would make them compliant. But today, like, I feel a lot like, obviously I wasn't alive in the 40s when hot rodding started, but I feel like this must be similar, right? Because, now everybody knows what to do with an LS. You can go to HP Academy and figure and learn what you need to learn. But the EV stuff, I mean, even the manufacturers and the OEs everybody's figuring it out, right? There's still lots of hot rodding to do. There's still lots of figuring out, and there's a bunch of resistance to change, of course, and there's a lot of just factual, like, there are some real challenges that should be acknowledged. We talked about safety, and one of the things we get, of course, is like conversations around safety. We've had great experiences at all the racetracks we've taken our cars to, but we've learned how to be successful at that. Meaning, we produced a 90-second YouTube video that gets circulated to the entire safety team long before our car shows up to the track. And we've reached out to the organizers in the track and talked to their safety people long before our car shows up at their track. So they know what to expect. They've watched our safety videos, so they know how the light behavior is. Because IMS, like FIA's dictated these things, and so IMS is following it, and Formula E is following it, and all the rest. But most of these track marshals still don't know it. They haven't had an IMSA event there.
Yeah, of course. So there's an education element that needs to come along to get them up to speed.
Yeah, helping ramp the safety teams, and even the safety teams that start like hell no. By the time we like, what can we talk? And we talk to them about what safety is built into the car and show them the video, and they're like, "This is great. Okay, cool."
Let's talk about a couple of the elements that I know maybe have been blown out of proportion, or at least have become big talking points for EVs, which the first and most obvious, of course, is thermal runaway. I mean, these things, when they catch fire, when the battery packs go into thermal runaway and burn, as I understand it, they're basically impossible to put out. So, anytime you hear that gets a bit scary. I will add the caveat here that, at least as I understand it, the chances of an internal combustion engine catching fire, a car catching fire, are probably, tenfold that of an EV. So that they are not alone in this ability to burn. But I think the scary part is, like, how do you put them out? So, can you address that and like what you've done there? I think you've already mentioned a fire suppression system, but yeah, what do you do to sort of combat that?
So what we've done with that is, inside of our modules, down to a module level, we pot the module with a fire suppressant foam. So HP Fuller is the company that makes this foam. And after the module is assembled and we've inserted our thermistors into the pack, which we have 96 little thermistors that monitor the pack in 96 different places. So we have very good granularity on how the pack is behaving. But this foam then seals those cells and it encapsulates them. So if you do have a cell that has a thermal runaway event, or you have a protrusion into the pack in, say, a very large violent accident, that only those cells that are affected go off and they have their little event. They do spark up, they do flare up, and that's what we have the Novec in the pack for. But what the foam does is, as the heat of the cell increases, the foam's insulative value actually increases. So it creates a little pocket that the cell cannot then light up adjacent cells, and you don't end up with a thermal runaway event. So this was very important for us to implement this safety into this pack. And when you see EVs that go into thermal runaways, they're very early type EVs. Most EV manufacturers have implemented this potting procedure after like 2017, 2018. You'll see a lot of the EVs have this, which comes into the effect why it's hard to modify a factory EV into a race car, because that battery, you can't do anything to it. Say on an older Tesla, you could open it up, you could add thermistors, you could add cooling, you could add plates, better chilling. You can't do that. You crack the lid open on a new battery and it's full of foam. You can't modify it. It's now useless if it has an issue, right? So ours, we've potted them to the module level so that the modules are replaceable. And that's how we've kind of dealt with the fire safety in ours. And Novec will go in. It's not going to stop a thermal runaway. We don't want to pretend that Novec 1230, we actually did the math with Lifeline. You would need, I think, 60 kilograms worth of Novec to keep that. And you're not stopping it. You're basically just suppressing the event while it happens, because you can't put out battery fire. It's a chemical reaction. It doesn't need oxygen to burn. So when people say it needs 30,000 gallons of water to put the battery fire out, that's just how long it happened to burn while you were dumping water on it.
The water wasn't actually fixing the problem.
No, and it actually made it worse, because now you just created a bunch of short circuits and now all the other cells start popping off. So the only thing it might have done is actually depleted the energy in the pack, so removed the energy from the cells. But all in all, it actually makes it worse. So you could put an EV battery in a pool and it just burns. There's nothing you can do to stop it. Now, we did come up working with some local fire departments. They have a very new strategy that actually is a very good implementation for EV battery fires. It's actually a blanket that goes over top of the car. Now, this is for production cars, but it gives you time to kind of deal with the car in a major accident. Now, in our car, what the Novec does is it kind of provides that blanket onto the battery. If you've had an event, a major accident, it gives safety crews time to get the car off the track, to deal with it, to get the driver out. Our motto is save the driver, save the track, save the car. If we can save all three, perfect. But it first and foremost is the driver. And then if we wanted the track to obviously to keep running. That's how they make their money. If they have a new crater in their track, it's not beneficial to anyone. So that was really important in the design of our battery.
Okay, cool. The other element, and we kind of have already touched on this, is electric shock. So you've got the indicator basically telling the driver and safety crew outside whether there's been a short circuit and basically the car's live and we shouldn't touch it. Am I picking up that right? That's how that works?
So the short answer is yes. The longer answer is it's worth actually understanding all the wives' tales around electric shock. DC current, its desire is to run pole to pole, right? Positive pole to negative pole to positive pole. And so if there is a short between the battery and the chassis, that light goes red. Like that is what it's doing is isolation monitoring. But that DC current has no desire to go to ground. So when you see all this IMSA bunny hopping out of the car bullshit, it's not, it's all theater. It's not like your house power, which is earthed to ground, has a desire to go to ground. And so you will get electrocuted if you go grab your house wiring. And that's an AC current going to earth on a system that's earthed. But DC wants to go pole to pole. So your likelihood of getting shocked from DC in an electric car would require that you close the circuit, and then that DC current will find the shortest path between the poles. And if you grab negative and positive, one with each hand, then that goes through your heart as a path, and you're definitely not waking up from that. So, but you have to understand how that works. So the likelihood is very low, and it's not going to ground, it's going to go to the pole. So you would have to have a short to the chassis of the negative, and then try to grab a positive pole somewhere, and all of them are hidden from you. And then the AC comes out of the inverter. So as Joel mentioned earlier, there's three-phase AC comes out of the inverter. Now there's only power coming out of that inverter when the VCU is running and the throttle pedal is being pressed to call for power. Again, in a crash scenario, everything's shut off automatically, but as an extra safety, you hit e-stop, like all that stuff's offline. There's not really a way for AC power to be coming through the car to shock you and try to run to ground, because the inverter would have to be running and calling for power. So is it possible? The answer is, of course, yes. Everything's possible in an edge case. Is it very likely? No. But generally, what we're doing right now is we're providing safety crews, or for a lot of the crews, because it's early prototype car, I'm going with the safety crew or Joel or whatever, and we bring high voltage gloves with us. So if there was a high voltage line sticking out, we'd be able to grab it and move it like safely, right?
So, I think really this comes down to just education, and I probably, like most people, would have assumed that there was a significantly higher level of danger in touching the car or getting out of the car if there was that breakdown. But good to know that while the chance of being injured is not zero, it is still very, very small.
It's still a race car.
Yeah. I mean, there's pretty much there's some level of risk in just about anything we enjoy doing, right? So it's about understanding and managing the risks. All right, I think we've probably got a pretty good understanding of what the car is and what Scalar Performance is up to. It's definitely been an impressive conversation so far. We'll move on to wrapping this thing up, and we've got the same three questions we ask all of our guests. We'll see how we're going to do this with the two of you, Joel and Brian. Maybe for a start, Joel, what's next in the future for you and Scalar Performance? I mean, we've touched on some of this, but maybe you could kind of tie a nice little bow around the whole thing.
So I think what's next for us, we're obviously being very fluid in our decisions and where the company goes and what we decide to do based on how the industry is moving. When we first started this, we wanted to build a car, have a spec series, go racing with it. But as we dove into the series, there's so much opportunity to be input into different areas in this space that we're really open to take our motorsports experience and apply it to many different areas. We want to take everything that we're learning, apply it into other programs. So as far as the future of Scalar, we want to take our knowledge and skills in the EV world and apply it to all the performance aspects that we can. So not only are we going to take our car racing, but we're going to take the technology we learned to this and apply it to every other industry that we touch.
Okay. Yeah, exciting. Our next question, let's go with you on this one, Brian. Is there any advice you'd give to a younger version of yourself to help reach where you are today in your career faster?
Oh, that's an interesting one. I think there's a couple things that have been very successful as a strategy, and one is networking, and two is don't be shy to ask people who have been there before you. Like the experts in the field, I've found I could have solved the problem really quick by just asking somebody if you're just not shy about it. And people who are senior in industry are often very generous with their time and knowledge. And you just need to be brave enough to ask.
This is actually a consistent theme that comes up in these podcast episodes. And I've talked about this before, but let me go again. At early days of my career, and I mean, I sort of did start, and I'm probably best known for my EFI tuning, and that is an industry that is so shrouded in secrecy and mystery, and no one wants to talk to anyone else, and everyone thinks they're the only one who knows how to do it. And I fell into that trap for maybe the first 5 years I was doing it, and then as you learn more, it's the Dunning-Kruger effect. To start with, you get a little bit of knowledge and you think that you're an absolute expert in the field, and the more you learn, the more you realize that you don't know, and the more there is to learn. And as I started reaching out and building a network of other tuners or other performance workshop owners even, and we would sort of knock ideas around, and I have a problem, someone else would have a problem. It's so good to have that network and be able to bounce these problems around, because the reality is nothing there is really new. Other people will have seen the same issues that you're facing, and you can shortcut that learning curve so quickly, so much by just reaching out, being a little humble, understanding that you don't know everything, because no one does. And I think no one would sort of think less of you for that. Last question for today. If people want to follow you, see what you're up to, how are they best to do so? What are your social media accounts, your website, etc.?
So everything's online at scalarperformance.com. That's our website. All of our handles are Scalar Performance on Instagram, YouTube, Facebook, LinkedIn. We're on all the socials. We post on everything weekly, and we're always doing updates, what new projects we're in, what the status of the SCR1 is. And just follow us on all of them to see how we develop this prototype.
We really are trying to share our learnings as we learn them. So
yeah, cool. Well, as usual, we'll put links to those accounts in the show notes to make it real easy for people to find. Look, Joel, Brian, it's been great to get some insight into the car. Great to learn a little bit more for my own benefit about EVs and all of the componentry that goes into them. It is literally so foreign from anyone who's sort of been brought up in the internal combustion world. So thank you for your time. And it is a great product. We really look forward to seeing how you guys progress and getting to this sort of spec class. So thanks again.
Awesome. Thank you.
Thanks for having us.
If you enjoyed this episode of Tuned In with Scalar Performance, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Vadir9 from the United States, who has said, best technical automotive podcast out there. I learned something new that I can apply to my 240SX project with every episode I listen to. There is so much great content packed into each episode. Thank you, HP Academy, for doing what you do. Well, thanks for the kind words there. Great to hear you're getting so much value out of the podcast. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.